Okay, today we'll go through the lesson for the gravitational potential energy.
Introduction to gravitational potential energy. An object has gravitational potential energy due to its position relative to the Earth's surface. Lifting an object from the Earth's surface increases the object's gravitational potential energy, GPE. The increasing energy of the object is gravitational in nature because work is done against the gravitational force of the Earth when the object is lifted. Examples of objects having GPE are water stored in reservoir and a raised hammer. In this lesson, you will be able to define gravitational potential V, derive the formula V equals negative G mE over R, define gravitational potential energy, understand the concept of equipotential surfaces, and derive the expression for change in gravitational potential energy. Gravitational potential at a point in a gravitational field is defined as the work done in moving a unit mass from infinity to that point.
That means that gravitational potential. Ladies and gentlemen, gravitational potential and gravitational potential energy, different thing, yeah? So today we learn that we will learn gravitational potential first, then we learn the gravitational potential energy. So these two things slightly different, formula difference a bit. So this means that remember, one, if gravitational potential is not equal to the gravitational potential energy.
Consider a mass m of 1 kilogram at a distance x from the center of the Earth.
So this means that consider there's a distance of x.
Move the mass towards the Earth through a small distance, dx. The work done is the product of the gravitational force F and the distance dx.
When it's moved, this means due to the gravitational force attracted, it's moved with a distance of dx. So it moved with a distance of dx, you see negative. Why negative? Because towards the Earth. Okay, that is an attractive force. Attractive force is negative.
Click on the mass m equals 1 kilogram to know the gravitational force of attraction between the Earth and the mass. F equals G mE over x squared, where G is the universal gravitational constant and mE is the mass of the Earth.
Previous lesson we learned that F equals GME, M object divided by the x squared. That means that the distance from the center of the Earth to the center of the object.
Click work done to derive an expression for gravitational potential V at a point P, which is at a distance R from the center of the Earth.
Gravitational potential is V. Gravitational potential energy is U. So difference.
dP equals F times dx. Gravitational potential V equals integration of dV over the limits infinity to R, which equals integration of F times dx over the limits infinity to R, which equals integration of G mE over x squared times dx over the limits infinity to R, which equals negative G mE over x over the limits infinity to R. Therefore, gravitational potential V equals negative G mE over R.
Okay, gravitational potential is GME over R. Okay, so if I still remember or not, so previous lesson we learned that GME over R squared, That is the gravitational field strength or gravitational expression if with R squared. Without R squared, this is the gravitational potential.
The negative sign denotes that the gravitational potential at infinity is zero and decreases for points nearer to the Earth. The gravitational potential is a scalar quantity and its unit is joule per kilogram.
So
Gravitational potential V equals negative G ME over R.
Okay, negative means that the gravitational potential at infinity is zero and decrease for the point near to the Earth. So that means if very far in infinity, that means very far. Okay, so that means we go to the next.
A graph of gravitational potential V against distance R from the center of the Earth is as shown.
Gravitational potential is almost to zero, right? It's now we notice that infinity means that the distance is very, very, very far away. This one near to zero, but not yet zero. Okay, so that means that when the distance reduces, so the gravitational, the magnitude increase. Okay, the magnitude will increase, but it's in negative. So negative GME over R.
What is the relation between the gravitational potential V and the gravitational field strength G at a point P? The relation is V equals negative integration of G dr over the limits infinity to R, which equals negative area under the graph of G against R. Also, G equals negative D over dr of V, which equals negative gradient of the graph of V against R.
Okay, so if there is a graph of V against R, if the graph let's say we have the graph. If first G against R and also V, gravitational potential against R. G against R, still remember it will be like that, right? Okay, so that means that the area under the graph represent the V. Area under the graph, area represent V. Okay, if V against R, just now V against R is like that, right? Okay, so that means that we find out the gradient of the graph V against R, the gradient will equal to G. Okay, this will be the gradient because the gradient, as we know that, okay, how to find the gradient for the, okay, what is that, for the curve. So that means that if at, let's say we choose a field point at this point, and this point, even this point. So that means that at this point, the gradient, let's say, is like that. At this point, the gradient is like that. This point, the gradient like that. And this point, the gradient almost near to zero. So that means that the gradient reduces. When the object is far away from the surface of the Earth, that means that the G will reduce. Okay, where this normally, this one here will be the RE at the surface of the Earth. Okay, will be maximum. Okay, let's move to next slide.
The plot of gravitational field strength G against R and gravitational potential V against R is as shown above. V equals negative integration of G dr over the limits infinity to R, which equals negative area under the graph of G against R.
Okay, for VDR, that means that if we wish to find the G, that means that area under the graph of G against R will be the will be the gravitational potential. Okay.
The gradient of the graph of V against R gives the magnitude of the gravitational field strength G. G equals negative d over dr of V. From the equation for gravitational potential, points at the same distance from the center of the Earth have the same gravitational potential. The surface on which these points lie is known as equipotential surface. Click on any of the cross marks to know the equipotential surface on which it lies.
Let's say first. Okay, so let's say we have 4 different positions. Okay, if let's say I use the green color, if this is the green color, that means that all the green color, no matter where is it, they will have the same potential. If there is a blue color, all the blue color with the same gravitational potential. For the orange color will always have the same because they with the same radius. Okay, and if there is a white color, that means that all the white dots, no matter where is it, they will have the same potential. So we said that this is the equal potential surface, known as the equal potential surface. This is the equal potential surface. Okay, get it? Okay, now
the direction of the gravitational field strength G is always normal to the equipotential surface.
Okay, the gravitational field strength, the direction is always normal or perpendicular to the equipotential surface, which direction is always to the center of the Earth.
Summary: gravitational potential V at a point in a gravitational field is the work done in moving a unit mass from infinity to that point. Gravitational potential V equals negative G ME over R. Gravitational potential is a scalar quantity and its unit is joule per kilogram. The area under the graph of G against R gives the gravitational potential V. The gradient of the graph of V against R gives the gravitational field strength G. Points at the same distance from the center of the Earth have the same gravitational potential. The surface at which these points lie is known as equipotential surface. The direction of the gravitational field strength G is always normal to the equipotential surface. A body in a gravitational field possesses gravitational potential energy. What is meant by gravitational potential energy?
Okay, just now we learned the gravitational potential. Now is the gravitational potential energy. Okay, so what is meant by gravitational potential? Just now we noticed that. Okay, gravitational potential. So is look at the
at a point in a gravitational field is the work done in moving a unit
Okay.
mass
So
from infinity to
how
that
to
point. Gravitational potential V equals negative G ME over R.
okay, let's say gravitational potential is a point, is at a point. V at a point in a gravitational field is the work done. Work done to move in moving a unit mass. How many kg? Don't know. Any object from infinity to that point. Okay. So work done, that means that, remember, it's work done to move a unit mass, any object from a unit mass. That means that, okay, let's say a unit mass, that means, let's say 1 kg. From infinity to that object. Okay, this means that, what is the meaning? Any object, okay, for 1 kg object, it needs how many work done, how many energy to move 1 kg object from infinity to that point. Means that, what it means that point? Okay, let's say now we have that this is the earth. Let's say I chose a few points. This is point A, this is point B, this is point C. Okay, VA, here is VA, VB, VC. VA, VB, VC, all of them are different. Okay, where VA will be greater than VB, greater than VC. Because VC, the distance is longer, right? RC, this is the RC. RC is longer, so that means VC is the smallest. So from here, VA, VB, VC, each of them with different value of gravitational potential. What is meant by VC? VC means that if there is an object, I want to put it to VC, to a point of C. That means that, what is the energy needed? Okay, the work done needed to put it from infinity, very, 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 very far. How far? Very far. Okay, that's all. Okay, to pull an object from infinity, its ability, the energy needed to move this object from infinity to this point. Okay, let's say this is, this is, okay, 10 joule. Okay, this is 5 joule. This will be 2 joule. That means to move it from here, okay, 2 joule enough. If to move the object from here to B, 5 joule needed. If this is 1 kg object. If move from here to A, that means I need 10 joule. Okay, so this is the meaning of the gravitational potential. Okay, that means that gravitational potential is energy. Easiest, yeah, energy needed to move 1 kg of object from infinity distance to point to a point. Okay, a point, this point can be point A, point B, point C. Any point, where is it? We can. So that means to a point. Okay, so this is the meaning of gravitational potential. Now we move to the next slide.
A body in a gravitational
field, this one already, right?
possesses gravitational potential energy. What is meant by gravitational potential energy?
Okay, gravitational potential. Gravitational potential is the work done to bring a mass from infinity to the point in the gravitational field. A mass of, okay, a unit of mass. Better.
The gravitational potential energy of a body of mass m at a point P, which is at a distance r from the center of the Earth, is the work done in moving the body from infinity to point P.
Nampak lebih kurang sama kan? Almost the same, right? But actually it's like that. Back to the example just now. This is the Earth. Okay, now this is point A, point B, and point C. Okay, to move the object. Now this object, okay, this object not 1 kg anymore, but with any mass. Any mass we known as mkg. Okay, so that means that just now V is equal to negative G me over R. Correct or not? Now the gravitational potential energy actually just now me, okay, actually times with m object. U will be also, okay, I use red color. U will be also negative G me mo over R. What are the difference? This m object, this one with 1 kg. This one is any mass, okay, which is not equal to 1 kg. That's all, the difference. Okay, so at the end we get that V is equal to negative G me over R, where U, gravitational potential energy, is negative G me mo over R. Okay, so later we go through the formula. We'll go through the formula.
The gravitational potential energy of a body can be deduced from the definition of gravitational potential as shown above. If m is the mass of the body, me is the mass of the Earth, and r is the distance of the body from the center of the Earth. From the definition of gravitational potential V at point P as the work done per unit mass, V equals negative Gme over R. Hence, the gravitational potential energy U of a body of mass m at point P is given by U equals negative Gme m over R.
Okay, so you see the difference. Gravitational potential is the work done to bring 1 kg of the object from infinity to a point. This one is the work done to bring any object with mass m. That means that the mass not equal to 1 kg.
A graph of gravitational potential energy U against distance r from the center of the Earth is as shown above. What is the relation between gravitational potential energy U at a point P, which is at a distance r from the center of the Earth, and the gravitational force F at point P? The relation is U equals negative integration of F times dr over the limit infinity to r, which equals negative area under the graph of F against r. Also, gravitational force F equals negative d over dr of u, which equals negative gradient of the graph of u against r.
If the graph F against R, area under the graph will be the gravitational potential energy. Okay, so that means that actually the F times with FdR, right? FdR, right? F times with distance. Force with distance will be equal to work done. Okay, that will be the energy. So if gravitational potential energy against R, the gradient represent the force, gravitational force.
The plot of gravitational force F against R is as shown above. U equals negative integration of F times dr over the limits infinity to R, which equals negative area under the graph of F against R. The plot of gravitational force F against R and gravitational potential energy U against R as shown. G equals negative d over dr of U.
So G, gravitational field strength or gravitational acceleration is equal to negative du over dr.
Summary. The gravitational potential energy U of a body of mass m at a point P, which is at a distance r from the center of the Earth, is the work done in moving the body from infinity to the point P. Gravitational potential energy U equals negative g m over r. The gradient of the graph of U against R gives the gravitational force F. Click on the car to obtain an expression for gravitational potential energy of the car on the surface of the Earth. Click the play button. The car is now at a height edge. Click on the car to obtain an expression for the final gravitational potential energy of the car at a height edge. U1 equals negative g m over r plus edge. Compare the two expressions for the gravitational potential energy of the car.
So when the car at the surface of the Earth, at the surface of the Earth, initial gravitational potential energy is equal to negative GME, mass of the Earth, right? Times with M, times with the mass of the car over R. So that means when it moves to a certain height, R plus H.
The change in gravitational potential energy, delta U, equals U1 minus U0, can be deduced on clicking the step buttons sequentially.
So this show that show that the relationship change of the gravitational potential energy.
U1 minus U0 equals negative G M over R plus H minus negative G M over R, which equals G M over R minus G M over R times 1 plus H over R, which equals G M over R times 1 minus 1 over 1 plus H over R, which equals G M over R times 1 minus of 1 plus H over R to the power negative 1. U1 minus U0 equals G M over R times 1 minus of 1 minus H over R, plus etc. neglecting terms h square over r square and higher as h is very less than r. U1 minus U0 equals GMEM times h over r square as GMEM over r square equals mg. U1 minus U0 equals mgh.
So as a result, from the derivation, that means that the U1 minus U0 is equal to mgh. This type of definition, the derivation, okay, is quite long. So we can use another shorter method. For example, as we know that, yeah, U, let's say U is equal to, okay, negative G M E M over R, right? So that means change of the, okay, difference change of the gravitational potential energy. That means that du is a change of the gravitational potential energy is equal to negative G M E M over R. The change is depends on the change of the what's that? The change of the okay. So let's say I do it like this one. The change of the du dr. Okay. So that means that if the change du over dr, change of the r. Okay. So that means that it will be equal to negative GMEM over R. Okay, over R. This, if I put another dr here, okay, if I put dr, that means this will be R squared. So from here, du will be equal to negative GMEM over R squared times with dr. I want to change it. U is like that. So du over dr has been divided by R. So now what I get it, change of the gravitational potential energy will be equal to negative G ME over R squared times with, okay, times with this one M. Okay, first, what is this actually? Where we will get that negative G ME M over R squared. This will be a force, right? Where it will be mg. So as a result, it will be mg dr. So that means at the end we can say that change of the gravitational potential energy will be equal to mg, because the object is, this will be the, okay, normally from the surface of the earth to a height, this will be dr, right? Okay, so that means that at the end it becomes mgh. Okay, this type of definition is more easier than the previous. Okay, so now let's move back to our slide.
Summary. On the surface of the Earth, gravitational potential energy of a body of mass m, U0 equals minus G MEM over R. At a height h, gravitational potential energy of a body of mass m, U1 equals negative G MEM over R plus H. When the height above the surface of the Earth, H, is very less than R, change in gravitational potential energy, delta U, equals U1 minus U0, which equals mgh.
Okay, here we have one condition, the h. The object, the h, is much smaller than the radius of the Earth. Okay, radius of the Earth is times 10 to the power 6, right? Okay, so that means that radius of the Earth will be, okay, consider is much bigger than the distance above the surface. Okay, so that means we just can use that mgh. Okay, so now as the summary for today's lesson. Gravitational potential V at a point in a gravitational field is known as the work done in moving a unit mass from infinity to that point. That will be the work done to move 1 kg of the object to that point. Gravitational potential is a scalar quantity and its unit is joule per kg. Okay, so that means that, okay, these are all the, okay, the information we need to know for today. And the gravitational potential energy is negative GMEM over R. And finally, the change of the